Welcome back. In the previous video, I had set up a problem of trying to find out a surrogate model for computational fluid dynamics. In this video, I will talk about one very recent solution. In fact, this is a very good paper. It is in 2016, created by people in Autodesk. Normally, I would have liked to show you the full paper. This paper is available online legally. I am just going to describe results from this paper. There are people within my lab also working on similar problems, but this is the original paper. I have taken sections from this paper instead of showing you the full paper, because it is a little bit convenient for me to show a few sections from this paper. So, please do read the full paper. It is very well written and the results are actually really impressive. Okay. So, what they used was, as you can see in the title, CNNs. Okay. So, the first trick that they have used, which I would like you to think about seriously, since CNNs have become extremely powerful over the last 5-6 years, is the fact that any field, this is the principle, any field can be interpreted as an image. So, to explain, the flow past a cylinder that I showed you in the last video, you can interpret this, if you just look at the contours that are shown there, as an image. Even the whole thing right now is just appearing to your eyes as an image. To me, as a person within CFD, this is velocities and pressure, etc., but to you all it is, in case you are not familiar with CFD, is just an image. So, we are actually going to exploit, or these people, these researchers actually exploited this fact that what looks like physics can be interpreted either as data or as image. Now, before we proceed, please remember that this interpretation is a little bit easy to apply in case you have what I will call homogeneous data, as in when I see a pressure contour here, okay, this contour or the colors that you see here represent just one physical quantity. I mean, it is not as if this portion is pressure and this color is velocity and this color is something else. So, when you have heterogeneous data and it is not field data, it is usually useful to use simple ANNs. CNNs are useful when you have images. Why is an image useful? Remember, the basic idea of a CNN is that spatial closeness actually matters, and we want to account for that within our weights or within our kernels or within our filters. Okay. So, what the idea was that these people used was the input is simply a section of the flow and it is taken as an image, and you will see the size of the image later on when I show you the architecture. They took one section of the whole flow. The flow can actually be quite big. There is one portion that you are interested in, you just cut that out and you take that as an image. Now, this idea of course is very general. I will show you another iteration of this idea when we discuss problem 3, but this idea of interpreting a field as an image is actually a very straightforward one. Okay. Now, when we take an image, please remember the image itself, for the sake of this particular paper, they took two images, one of the x component of velocity, another one of the y component of velocity. Both these you can just take as images. Okay. Now, these are our outputs. I am sorry, I should have called this output rather than input. So, what we are interested in is actually the velocity of the flow as output. Okay. Now, what is the input? This is a little bit more interesting. Okay. Now, we know that what causes the flow in this case, for example, is the shape of the body. Okay. Now, the shape is a little bit vague. Now, I want to, if I change this shape to let us say a square, as a fluid mechanics person, I know that I am going to get a different flow. You might know this, or you might even see this intuitively even with even if you are not within fluid mechanics. So, the shape is what determines the boundary condition, the boundary condition is what determines the flow finally. Okay. So, if I change the shape, the flow changes. So, that is the input, but how do I give it? Okay. So, we know that this is supposed to be the shape, but how? Okay. So, we have several options. Let me give you a couple of options. Actually, the people within the researchers within this paper themselves considered it. So, one thing is they had decided that they are going to give they are going to use CNNs. Okay. So, that much is decided. Once you have decided that you are using CNNs, pure CNNs, you have to give an image as an input. Okay. That is also determined. The special thing here is we have an image as output also. It is not a classification, it is actually a full image, just like you saw in segmentation tasks. Okay. But the input is also an image. So, how do we give an image as input? Okay. So, let us say I want to give the image of a circle as an input. There are a few ways of doing it. One very simple way is to say, let us say this is 256 cross 128 pixels, and within each pixel I will label it as 0 if it is inside the body, and I label it as 1 if it is outside the body. Okay. So, is this clear? 0 if inside the body, 1 if outside the body. This is one possible input. Now, as it happened, when people did this, when the researchers did this, the results were kind of okay, but not so good. Okay. So, remember, when I have this kind of problem, what I am saying is for a specific input, I am going to somehow map it using some CNN architecture to an output, image to image. Okay. I am not going to talk about the architecture right now, I will talk about it in a few minutes, but somehow if you are able to map this input to an output, they saw that if you label the input as zeros and ones, it does not work very well. Now, why does it not work well? Here is where your domain knowledge comes into play. Okay. Now, we know from fluid mechanics that it matters how close you are to the body. Okay. Perhaps you can see this even if you do not know fluid mechanics, the further and further away I am from the body, the lesser and lesser it will matter what the shape of the body is. Okay. Similarly, if I am close to this body and I label that pixel or location 1, and I am far away from that body and I still label that pixel or location 1, then it seems like some portion of the physics of the problem I am completely throwing away. I am saying that this portion of the body or this portion of the flow is as important as this portion of the flow as compared to the shape of the body, which is not true. So, these people actually came up with a slightly modified idea, it is an intelligent idea, it is called a signed distance function. Okay. What is a signed distance function? It works as follows: inside the body it will be negative, outside the body it will be positive, and the value will be the distance closest distance from the point to the body. Okay. So, suppose you are at this place, they will find out the closest distance from there to the body, and if it is outside they will label it positive, if it is inside they will label it negative, and this way you have something that accounts to for the fact that points that are close to the body are actually more important than points that are further away from the body as far as the boundary conditions are concerned. Okay, let me show you a contour for this. So, you can see here once again they have drawn this signed distance function exactly for a circle as I have shown here. You can see that 0 distance is this dark blue. So, somewhere here is where the body is, farther and farther away is more and more positive, inside is negative, and you can see this body. Actually they have shown the outline, this is actually the body. Okay. So, the body is here and this is how they have given the signed distance function. Now, for any object you can give a new signed distance function, let us say it is an airfoil, once again negative here, positive here and then find out the shortest distance from any point to the surface and then label it positive or negative. Okay. So, this is how they have given the input, and once again here is where we have used some amount of domain knowledge. Okay. Now that we have decided the input, we have decided the output, we need to decide two more things. We need to decide the loss function, and finally, and in some sense most importantly, you have to decide what is the architecture, what map, what model are you going to give mapping this image to the image of the flow. Okay. Okay, so, let us first discuss the loss function. Okay. The loss function is very simple. For each flow I have my ground truth, this is of course in the training set. The ground truth is the CFD solution. Okay, so, you have some code, they used something called LBM, lattice Boltzmann method, in order to generate lots of flows. Okay, so, they found out CFD solutions, and you have your prediction. As usual, let us call this y, we will call this y hat. So, the loss function you have several choices, I will just mention one that you could use, y minus y hat square by 2, of course this is our least square loss function, except with a small change, we will multiply it by one small number, I will just call it in or out. We obviously know that the flow within the body, okay, here even if the CNN gives a prediction, that is actually useless. Okay, so, this here we have no flow at all. So, even though you are still, since you are interpreting the whole thing as an image, you are going to get a loss inside the body, that part we will not count. Okay. So, in means we will use 1, oh sorry, in means we will use 0, we will not count the loss, out means we will use 1. Okay. So, that is only loss outside the body is calculated. Okay. Another way to say it is, if the sign distance function is negative, you will assume that there is no loss, and if the sign distance function is positive, you will actually calculate the loss and incorporate it into the architecture, into the algorithm. Okay. Now, the last step is we want to find out what the architecture is that maps input to output. Okay. So, let us see that. I am going to give a rough architecture now, and then I will show you the architecture that they used. Now, remember we have an image as input, this image was the sign distance function, I will call it SDF, this was a 256 cross 128 image. We also have an image as output, again 256 cross 128. Now, you have two possible images that you have to give. One of these will be the x velocity field and one of these will be the y velocity field. Okay. Now, once again it is our domain knowledge that tells us that there are effects of two things. One is the effect of physics, which is the PDEs, and another one is the effect of the geometry, which is given by the boundary conditions. So, what we will do is we will use, first thing, remember that I want to go from an image to an image. So, typically this is very similar to what you did in segmentation tasks. We will use what is known as an encoder-decoder structure. You would have seen this several times during the CNN lectures. An encoder-decoder structure does the following: it takes an image, squeezes it into some essential information and then expands that essential information. It is sort of like zipping a file and then unpacking it. Okay. You just remove the unnecessary stuff, pack it into something and then expand it. Okay. Now, what it does is essentially only the important patterns stay and the other stuff goes out. We will do the same thing, encoder, decoder back into the full image. Okay. Now, An important thing is, should you use 2 encoders and 2 decoders or 1 encoder 2 decoders, etc., because remember we are trying to predict 2 things, and here is where our physics knowledge comes into play once again. We know that when I am encoding, what I am encoding is effectively the geometry. Okay. This is not strictly speaking true, but it is true enough that I will just leave it like this. Okay. So, what I am saying is, regardless of whether it is the u velocity or the v velocity, your geometry has to be squeezed. Okay. So, therefore, this can be common. Because it only pertains to the geometry and not to the particular velocity field, and the decoder actually tries to incorporate physics, and then you can split it into 2, ux and uy, 2 separate decoders are used, and of course, the corresponding loss function. Okay. So, let me actually show you the structure that they used in their paper. Here is the CNN architecture that the people used in this paper. Now, notice what is happening here. This portion is the encoder until here, took a 256 cross 128 image, squeezed it and got a fully convolutional, a fully connected layer of 1024. Now, this portion is the decoder portion, and you have split it into 2 sections, one is for ux and one is for uy. Okay. Specifically, also see that you have 128 in the very first layer, 128 filters, okay, each of size 16 cross 8, which is why this 256 cross 128 now got squeezed into 16 cross 16 cross 128. As a simple exercise, please think about what is the stride here. Okay. The stride, as you will see, is actually 16 cross 8. Okay. So, what it is doing is, it is taking a block, it is not simply sliding, takes a kernel, it jumps and comes down. I will leave this to you as a simple exercise. Dr. Ganapathy had discussed this in great detail, but this is just so as to avoid too many filters and too much computation. Okay. So, this is a simple structure. Similarly, the next step is to use 512 4 cross 4 filters, and finally, there is a fully connected portion, and like I said, it is possible to interpret, though not quite accurate, to think of this as squeezing the geometry. The reason it is not quite accurate is we are actually doing backprop throughout. Okay. So, some effect of ux and uy is actually going to go through. Okay. After this, they have a decoder structure. Okay, you have transposed convolutions, you sort of expand this back, right back to the same original size of 256 cross 128. You would have seen this several times during the segmentation task. Finally, we take the loss function, you get x component of CFD, you get y component of CFD, and then you train this. Okay. So, once you do this, the results are actually quite surprising, and I would like you to see these results right now. Now, this work by Guo and co-workers, what they did was they used simple shapes, the kinds that I had described earlier, for which CFD tends to work a little bit fast for several technical reasons. They used circles, square, triangle, etc., some polygonal shapes, okay, and oriented them at different angles and found this out, and found out various flow fields, and they actually gave far more complex shapes, such as for testing. So, this is for training, and what is remarkable is, unlike our usual CNN examples where training and testing actually in some sense look similar, they tested on far more complex shapes. If you know CFD, you know that from here to here mapping is actually quite hard. You can't really say something quite obvious about this. So, cars, wings, etc. Okay. Now, I am going to show you their results. Again, I would refer you back to the paper. It is a very good paper. It is available for free for academics as well as non-academics on the web. Please search for it. Okay. So, here you have their results. what is written as LBM is essentially CFD, we can take this as ground truth. Okay. And here is the prediction from CNN. You can see that, picture to picture, the match is actually remarkably good. This is actually extremely good. Their error was around 1 to 2%. So, you can see the error drawn here. Now, as a person in CFD, we know that these things can be somewhat worrying. Okay, so, there is some error near the boundary, which is actually important for people within CFD, but nonetheless overall this is actually a remarkably good prediction. The speed up is actually quite huge. Okay, so, speed up of order a few hundreds. Okay, depending on whether they used CPUs or GPUs, their speed up rates were quite different. So, this is actually an excellent surrogate model. Okay. Why is that? Because you can get up till 2% of the answer, at least in the whole flow field, you can get up to 2% of the answer about 200 times faster. So, you can imagine if your design cycle is predicated mostly on CFD, it is not always, but let us say 60 to 70% is actually dependent on CFD, you can actually get a speed up of a factor of 10 or 15 in your whole design cycle. Something that takes an year can take about 20 days. So, you can see that just by using CNNs you can get really rapid, this is of course this for some limited cases, we are not there yet in terms of full 3D and all sorts of other complexity flows, but this is a great beginning. So, I would refer you all to this original paper by Guo et al. Whether you are interested in CFD or not, of course, I spent a long interminable amount of time talking about CFD, and I will briefly introduce the next two problems because they are somewhat related, but in general CAE problems, CAE being computer aided engineering, okay, CAE problems in general can gain tremendously. People even within chip manufacturing companies, all of them do some computation or the other, and CNNs have tremendous applications there. I expect more and more papers, and indeed many papers have come out over the last year. This was 2016, 2018 to 19, many papers have come out, and by the time we finish this course and by the time we finish this year, you will probably see the literature flooded with such examples. I encourage you to just look at CNN application of problem X wherever X is a field problem. Thank you.